started. So BPM and JS, the thing is, most of us already have an idea of what BPM is. It's beats per minute, and we know it's a generalized tempo measurement for songs to see how fast or slow it is. But if you really look around, historically it's been a very manual process. You have people labeling the actual beats and uploading profiles to databases to make this data available to applications, and that's just not ideal in a world where things are changing so quickly and we want this data available readily. So I wanted to look into, number one, how to make this an automatic detection process. And second of all, just trying to bring it into the JavaScript world so that we can all use it. First things, just a little bit about myself. Right now I'm working at Twitter in the New York office as a software engineer on the web team. My name is Janessa, if you didn't catch that from the first slide, and the program. And previously from that, I come from the background of computer graphics and vision, and then before that, a lot of bioengineering, where I mostly hated the bio and mostly liked the engineering. So what are we really talking about here in terms of what's behind automatic detection of BPM? Well, in research, they call it onset detection. So if you look at the signal that I have here, what we have is we're looking for this thing. We're looking for when the beat happens, there's a really sharp signal change, and we want to see where that is to know where beats are happening. So what this is fundamental to is like a million different fields, and that includes sonar, speech, EKGs, movement detection, and some things maybe like Iron Man. I think I secretly wanted to put him in my slides too. So, but seriously, sort of. So Discover ran an interesting article about becoming Iron Man. How close is research to really making these suits that you can control, with your nerves? If you're into the comic books, that he installs stuff into his body to interface. And that involves things like EEG or electroencephalography, which you're detecting onsets for the nerve signals, and you do a lot of analysis after that. But you get the point. This is a very fundamental sort of applicable thing, not just to music, but a lot of things. But since I'm a music nerd, personally, I like to think of it, this is a much more interesting application that I want to look at, which is automatic transcription of music. The first step is detecting your beats, of course, but there's also things like instrument identification, instrument isolation, pitch projection dynamics, all things that I plan to hopefully in the future look into as well, and by reading lots of research papers and stuff. So why did I want to bring it into the browser? There's C implementations and research being passed around of this stuff. Well, the biggest thing is I find research papers and this whole academic research area to be so niche and closed and entwined in the politics, and people never really look at research papers. I wanted to bring that sort of engineering and make it accessible and shareable and cross-platform and make it easy for all of us here to just use and play with. And the other thing that enables this is that the browser JavaScript is seriously fast now. It's no joke. This article that ran earlier, and that's really just it's just helping us to do things that are really computationally heavy without having to worry about delays and lag time as much. And with things like we just saw so much going on with WebGL and web audio. And digital signals processing is really enabled in the browser now. It's pushing that forward. We can do a lot of these computational things, which makes the browsers really powerful. You can do so much awesome stuff. So the caveat, of course, is all these things are great, but they only work in the latest and greatest Canary beta, new shiny builds of. I'm sorry about that. I meant Chrome, Firefox, Safari, and Opera, and that was a little bit mean because IE really is coming along with that. But also, why in the browser? Well, when I was thinking about doing this, honestly, this was the biggest reason. I think JavaScript is fun. I think this stuff is fun, and it would be cool to play with, and I think that's the best reason to start working on something. And another thing to note is that the browser is really diverse now. It's not the 90s anymore for document display, where the most interesting thing I could find was, unlimited GIFs of Sailor Moon or GIFs or whatever. And more importantly, the community is really diverse. We've seen such a great subset here of the JavaScript community. Everyone comes from such different backgrounds, from art backgrounds, music backgrounds, all sorts of engineering. And because of that, we're really pushing the use cases of the browser and what we can do with it and what it's becoming enabled for. We're influencing it by making people who are on the standards community think about the different things that we want to do with it besides displaying all the animated GIFs you could possibly find on the internet. My personal mission in terms of this little diversity thing is I come up from an engineering background from my undergrad. I'm a huge music nerd, and now I'm doing full-fledged computer science web development. So I like to put this in my bio. Finding ways to breed engineering, research, music, and art with the trusty steed of JavaScript. That's JavaScript, not Horse.js. To make the magical unicorns of my imagination a reality. So I found an image that sort of like captured my mental image. I wanted to share with you. So just in case you didn't know, this is the magical unicorn I'm going for. Breathing fire, like epic with eyes. And that's me. That's the cat riding the epic magical unicorn. And there's a little neon cat in the back. If you missed that, I thought that was like really awesome. But this is like living the dream. Like I'm gonna take engineering and smash it with art and music and JavaScript, and it's gonna like look awesome. But so far, because things are coming along, a lot of my projects end up looking like that. What is he saying there? I must eat more rainbows. Like they're a little bit lumpy and awkward right now, but we're getting there. And it's still a lot of fun. You still have a unicorn. It's just in kind of awkward and derping. But anyways, let's jump in. Let's breed some unicorns. So this is a big question, right? How do we do onset detection? Like, what is this? First, I want to take a quick step back and think about, BPM. We think about it because DJs are like all popular now, and BPM, it's like that, thump thump that you hear on the bottom. But it can mean a lot of things. It's really tied to human psychology, and it can be anything from percussive beats, which is what we think of. It could also be pitch and notes. You have like a flute piece from the classical music era, and it's like you don't have a drum in the back, like and sing, like in a club. So. Onsets, this is just a little bit of research terminology. They like to categorize it into a lot of different names because it is more complex than just detecting where the drums are. So there's pitched or not pitched percussive, and more commonly now it's complex mixed, which is basically like everything else because they can't label everything. Some quick sort of just scoping. A lot of times BPMs are associated with genres these days. For example, drum and bass, they like to say it's like 160 to 180 and et cetera, et cetera. And if we're talking about classical music, if you have a background in it, I did piano for 14 years. So this adagio, for example, is 66 to 76 BPM. It's not just this new DJ thing like matching BPMs in the club, So detection method. So how do we do this, and how did I learn how to do this? Well, I read a lot of research papers, and I'm not going to read this out to you right now. But I think this part was actually a lot of fun and interesting, understanding some esoteric language. So I'll break it down into something sort of bite-sized for this talk. So first what we're doing, there's some general steps. We're doing an STFT, short-time Fourier transform, which basically the purpose of it is to prep the signal for detection functions. Then we do the detection function. What these are functions that are meant to selectively maximize for onset properties that we're looking for and turn them into strong signals we can pick out in peak picking, which after you have those highlighted onset times, you can pick out those times from the signal that you've now got all like processed. And from there, it's home free. You calculate the BPM. So I'm not going to go too much into the mathematical detail of things, but I do want to show you a high-level view of what this looks like, just so you have an idea of what I've tried to stuff into JavaScript. STFT does a number of steps. It's not just a Fourier transform. It does window slicing, slicing the signal into overlapping windows, often for this application as small as 50 milliseconds, 80 milliseconds. And then you apply Hamming window to trim off the edges of bad stuff, basically discontinuities, and normalization, normalizing the magnitude, and zero padding because it needs to be a power of 2 to do an FFT on it, and it clarifies the signal. You can get into that if you want on your own. And then finally, you do your FFT and get a bunch of complex numbers in a matrix. So detection functions, what these look like, I'm going to go over the ones that were frequency-based because they were more robust out of some of the ones I looked at, and also these seem to be the ones that are more prevalent, more robust, got recognition. High frequency content and spectral difference. I stuck the math in there if they're math and engineering nerds and want to like dig into the summations. But these two maximize on energy, which tends to be those percussive beats. Phase deviation is more sensitive to things like pitch, and Euclidean distance tries to smash these two things together into something a little bit more balanced. So, we're looking for that onset there, trying to highlight it. Peak picking, there's a few, it's not as simple as you would think, just because the signals are noisy and you're doing processing on them, they're still going to be noisy. So you're building an adaptive threshold, which you'll kind of see the visualizations later that I have for this. And by applying that threshold, we try to cut out the noise and actually pick out where the onsets are. So initial peak finding, you threshold them out, and refractory period is another way of filtering where you say, oh, there's no way that there can be a beat between this time and this time because it's too short and it's probably noise because they're right next to each other. So this helps to cut out some of those noisy signals if you pick some of your windows wrong. And not to bore you too much with the nitty-gritty details of this, but peak times, this is a trivial example, but say I have a bunch of peak times. So it's really simple from here. It's about 0.5 across the way. I average it. And there's a beat every half second, and that's about 120 BPM. You missed the happy unicorn. I pressed next. Well, I think the unicorn, I had high hopes for my unicorn. How do we do it in JavaScript? I'm going to go over some of the fun things I ran into. They're kind of fun. Oh, but before that, I tried to think of some interesting things I could do with this initial implementation. And I found one song that I particularly like. If you don't listen to Discovery, they're fantastic. You should look them up. But So Insane by Discovery, they do an interesting thing where in two spots in the song, they kind of dip it down into a lower BPM and like slow it down and make it like all groovy. And I wanted to see if I could maybe pick that up by slicing it into 10-second signals, or 10-second windows of signals and pushing it through and seeing if I could see a modulation. I assigned some colors to it. Where darker means a slower BPM and lighter means a higher BPM. And I found that these two patches, they're 10-second signals, so it's still pretty granular, but it actually picked up pretty closely to the timestamps on the bottom where these were happening. So I was really excited about that. I wanted to show you. So tools that I used that were really helpful, just being like, how do I bring this research paper and put it into JavaScript? And dsp.js was really helpful. I didn't have to write my own FFT algorithm. It's been done, it's been out there, and people have been using it. I used it also for my windowing function, so that was super helpful. There's a node, actually, no, there wasn't an NPM version. I've had to do some interesting wrapping of the stuff only that I needed and taking it out. But web audio does great things like how I used it in its most rudimentary form is you take a signal, you throw the file at web audio, and it will spit out a sample rate and a float32 array for me to work with, which is great. Complex arithmetic, you do have to do complex math with this, so I found a handy NPM module so that I didn't have to write that too, because that would just be silly to reinvent the wheel. And a lot of the other stuff, I just had to kind of write a lot of math and stick it in a lot of loops. So for that, Browserify was a huge help for me, just being able to keep my code organized and sane so I could see what was going on, see how things were connecting. Clear thing about how it actually connected together. BPM, that was my main driver module. Web audio, as I said, feeds a signal and information in. And these were the three things I went over before. So I separated them out according to what I saw. And a lot of the math was happening there, so connecting up all of those things there. And detection, I had the for detection function. So this is much easier to, Browserify, I just really like it. And source maps are awesome. So interesting challenges that I ran into. This is a little anecdotal, I suppose. I've never really had to work with float32 arrays before this. So that was interesting because I realized, you can't just add zeros onto the end. You have to slice it and copy the array buffer and stick it in a thing that's bigger. And so that was interesting to learn about. And I mean, that's the best thing if you're learning when you're building new projects. So it was fun. But compatibility, web audio is enabled right now in Chrome and now also in beta versions of everything else, which is great. But that's something that you kind of have to be realistic about. And then complex arithmetic and matrices, coming from engineering where MATLAB does everything for you. They have a function to do the most complex things in matrices and it just spits out answers. JavaScript's not built for that, so I had a lot of verbose pushing stuff around, beating it into JavaScript form to make it really pop out the complex stuff that I needed. And the biggest thing was just figuring out how not to break Chrome. I have an optimization slide later where I know I haven't addressed a lot of the optimizations things that I wanted to do but didn't quite get to. So I'm aware, but it was really interesting. So there was a lot of this where I accidentally put a debug statement in a place that I probably shouldn't have put a debug statement, but it was late at night. These are those complex objects from that library, and it was 4 windows in, and it was and I tweeted it out of frustration. Of course, my snarky coworkers are like, well, look like you're doing something complex. Well, there's your problem. I'm like, thanks. It's 4 in the morning, not encouraging. But literally, it would get to the point where Chrome started showing me measurement rulers randomly, and they would get stuck. It'd be by the way, your window is blah blah. I'm I've never seen this before. What did I do to it? My poor Chrome is crying at me, and after a while, I would hit localhost 3000, and literally it would just immediately crash. Be no, I know what you do at this address. You can't do this anymore to me, and just stop. But that was interesting. And looking at these arrays, there's a lot of dots behind this tweet where it's thousands of indices that I was kind of scraping through. And you make mistakes doing math.pow late at night, doing math.pow number 2 instead of 2 number, and et cetera. So I was getting a lot of these, na 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 na. And when you're, seeing a lot of these late at night, in my head I was na 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 na, Batman. I was God, I'm going crazy. Someone save me from the nans. So these were some interesting nights, me and Chrome happy together in Batman. Anyways, enough of that. You get the point. All right, so here's where I'm going to I stuck a lot of little plotter things in there to help debug, and I think it really illustrates what's going on in this signal and to see all the math stuff that I did before in action. So I thought that would be helpful to kind of show my code working and crunching these numbers and shaping them. So this is what the original signal, something like this, would look like. It's just plotting the signal. Hamming window, trimming off the edges, as I said. Then the normalization, the numbers are tiny, but there's 1 at the top of that. And 0 padding, as much as you want. And then FFTs, you saw in the previous screenshots, just complex. They're complex numbers. This might be a little bit small, but there are actually not that many lines of code. It was just a little bit of wrangling, working with float 32 arrays, as I said, padding the signal is not just push a bunch of zeros at the end. It's no, there's an array buffer and then a view on top. So things like that. FFT, this would have been so much longer if I didn't have DSP, so God bless DSP.js. Same here for the detection functions. I'm just going to bring them all out here. So these are the 4 that I covered before, kept the math there. They're actually not that bad. Once you learn how to read mathematical and discrete notation, you can do so much with it. So maybe I'm echoing other people, but don't be afraid of this stuff. It's just a couple lines of code, Not bad. Unicorn's still looking pretty good, I thought. Peak picking. So this is what it looks like after I've applied a detection function. I've done the Euclidean distance one here. So you see that you have some strong peaks going up here, and that's detecting where those onsets are happening, and it's really spiking the signal up there so that you can pick this out afterwards. Here is the median filter step. This is part of the thresholding. What it's doing is it's smoothing over the signal according to a window size so that you can kind of filter out a lot of that noise that's going on that's just interrupting seeing clear peaks like that. So after it's filtered, it's a lot clearer, it's flat like that, and you basically choose out the peaks, and et cetera, and you have an array of times. And like I showed before, you take those, and what I do is I take the gaps, average them, and do a little bit of math, and you have a BPM for your sample. So here's my optimization and performance slide, how not to break Chrome. I know there are ways, and I just haven't quite delved into it yet, but I'm excited to soon because I want to fix a couple things. But web workers, I think, are just ripe for this sort of thing, especially for the short time Fourier transforms step, where I have like a gazillion 50 millisecond windows. I'm doing the exact same thing to every single one of them. So pass them into a web worker. As far as I know there's like an exception for typed arrays as well, where you don't have to serialize and deserialize it, which just slows everything down. And I'm using typed arrays, so if I can just pass that through, process all the crap, and pass it back, like that'll be a huge performance gain for me. Most music songs don't change in tempo or BPM. So if I slice well-selected windows, I don't have to process like a 10-minute song all at once. Like, take it one from the beginning, middle, and end. Like, I think I could basically figure it out, and that would save just a ton of computation. I have a third point that didn't show up, but it's basically about ASM.js, and LL.js. It's perfect for this, and I've just started learning about it, so I might go back and like rewrite the whole thing in LL and see what happens. So we'll see. But I thought this was interesting. So I tried out a MATLAB implementation, and MATLAB is like the engineering dream. It does all the things with matrices all at once for me. Median filter, like I wrote a median filter. That one, it's like median 1 signal, window size. It's like one line. I'm like, wow, I wish I could do that in JavaScript. I guess I'll have to make it so people can do it in JavaScript. But it was cool because I was testing with signals on both of them, and they actually take about the same time. It's not like MATLAB is like exponentially faster like I thought it would be. I think a 10-second signal I tried, it was like an uncompressed wave or something. It took like a couple seconds in the browser, which is not bad. MATLAB was about the same. It's like busy, 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 and it spit out some stuff. So I was really encouraged by that. Like go JS, love it. And the dream here is if I can make it fast enough, like all of this processing stuff with like the heavy computation, it's always been like something I post back and it generates and generates. It's like, it's been a couple hours, can I fetch it yet? Like there's a queue, can't fetch it yet. But if we could do this like all on the client side and just like process almost real time, I think that would be super powerful just for anything you think of to do this with. Oh, there it is. ASM, Scriptum, LLJS. If you were here for Brendan's talk, which was epic, you know about all that. All right, so there are some weaknesses that I need to be realistic about, and these come straight from the research on onset detection. You might have heard me mentioning things like the median filter, window time. The window slicing could be 50 milliseconds or 80 milliseconds. And the thing is, if you use those wrong, like you just make really giant windows, or you filter out that thing so it's so smooth, like you eliminate all the onsets, like you are going to break this. Like it will give you crazy numbers that make zero sense. So that's just something to be aware of, and something that I still need to test different parameters for different detection functions to see kind of where I can apply them and where I can't. And so and this feeds into that, prior knowledge is often helpful to selecting the right detection functions. Like I said, some of them are pitch-based, so if you have like a flute piece, like the percussive one is probably not going to do that well on that, but phase deviation might. And there's still a lot going on in research, so there's lots of reading to do, and just more things to look into. So future work, just on the more general side, besides wanting to make it faster, this is really only scratching the surface of research. Like I read a couple of papers, found some good summary papers that summarize a lot of the things going on in the field. But there's so many more detection functions that people are developing every day. Like this is their full-time job. They're PhDs, like underfed, underpaid, and this is what they do all day in the lab. And I almost went into research, and I'm glad I didn't because I don't have the personality for that. But God bless all the people who do. Like this is crazy, awesome stuff. And as I mentioned previously, for different applications, onset detection exists. It's just forced signals. So really, the only difference is yanking out the detection functions I'm using for music and sticking other ones in, and maybe other things that I just haven't read up on, onset detection for nerve signals and stuff like that. So, grading time. So how did I do? Was my JavaScript music engineering, stuck together and taped with Scotch tape unicorn beautiful? Well, it's a little bit forced. Like I have to admit, like I felt like I was like sticking, because engineering as a cute pug and into like a JavaScript horse suit and it like grew a horn and some like fuzz. Like it was okay. Like there's a lot of things I can do better. Hopefully like clean it up, you know, put more skin on it, and it's like it'll be good. Like we're really getting there with the browser. The web is changing aggressively, and you know, just as a quick example, I was just searching around NPM for stuff to use and just to see what I could find. When, you know, very like basic engineering sort of keywords: DSP, digital signals processing; FFT, which is the fast Fourier transform; filters, a little less there, but there's a lot of stuff out there for free that people are using every day, downloading, maintaining. You know, like this is really awesome stuff. Like it's available for us to play with and use and improve upon and contribute to. And God bless NPM, because I just did a search and I found everything I needed. So, and things like, you know, web audio and, you know, the W3C really pushing forward on a lot of these really powerful tools. And, you know, DSP.js was like written forever ago, but glad I didn't have to do it, someone else did. So, and it's a lot about, you know, rethinking web engineering. It's like, I thought that when I left biomedical engineering, because I hated bio, it's like, oh God, I like learned all of this electrical engineering stuff for nothing. Like, what am I going to do? But you know, yesterday I built a robot with like a breadboard, like the old days, and like, you know, now I get to use this stuff in the web. Like, you know, I didn't have to leave all that behind. So, what does it mean to be a web engineer these days? How about more engineering? Like, you can bring all of these things that you've learned, or if you want to learn, like, there's stuff out there to learn. And you know, we're all smart people. That's why we're here. So, how about more engineering? This kind of stuff, like vendor prefixes, is not the final frontier anymore. I know a lot of people, you know, friends in New York who have come over from finance, like completely different fields, having no idea, and they're like, oh my god, like, look, I found like CSS transitions, and I'm like, that's really nice. Now let me show you something on NPM that's really fun to play with, that you should play with, like that whole connect talk earlier. Like, they would have so much fun with that. Like, you know, these are cool and they're important, but like, it's not the final frontier. Like, there is things beyond the vendor prefix cacti, and it's thorny in the vendor prefix cacti, but that's another topic. I think it's just really important, and I mean, now towards the end of this conference, I feel like this is not even necessary to say anymore, but you know, there have been so many diverse talks just, you know, today and all of the other days, and it's really important for us, I think, to embrace diversity. Like, I think that this field is young enough, like, you know, web engineering and JavaScript, that a lot of the people that I've met here are really diverse. They come from engineering backgrounds, art history backgrounds, music, you know, like fine arts, anything you can think of. They've done it. And I think because we're such an open community, like that's what we're known for, we really need to embrace that and bring it together and collaborate on all of our different talents. You know, knowledge really builds upon itself, and combining these fields generates a lot of powerful tools. Like, you know, you don't have to figure out everything yourself. Like, your peers have done this. Like, you know, like Raquel, she worked on robots for years and years. Like, she can answer all of your questions. Just ask, you know. And, you know, just thinking outside of the box, like I said before, like, you know, I do web engineering at work all the time, every day, but in my free time, you know, I want to do something different. But it's still things that I know, the web and other things, but it's really exciting and a lot more fun, I think, for my free time to just think outside the box. So, you know, breed on, unicorns. And that's all I've got. And I just want to say again, like, I really look forward to seeing all the diversity that you can bring to web engineering, and, you know, show me what you want to do and what you can do, and I think we'll all be better for it. So, yeah, that's it. Thanks.